Welcome to Domain 4 of the ENSLD Blueprint. We're going to kick things off here with a couple of skills around quality of service. In fact, Cisco on their blueprint, they break it down to two different sections, 4.1 being QoS Strategies and 4.2 being QoS Policies from an end-to-end networking perspective. So we're going to treat this a little bit in a way as one large conversation between the two skills. So if you're not working your way through the ENSLD course, then you might want to make sure that after the strategies conversation, you go have the policies conversation in the very next skill within this course. Within the context of this skill, we're going to be talking about why QoS is so important, as well as taking a look at the different models that we have available to us, such as int-serve versus dis-serve. We're also going to dive into the start of a conversation around how exactly QoS happens, specifically around classification and marking, as well as queuing and scheduling. So come along and with me, we're going to explore how exactly QoS is used in our networks so that we can then turn that around and make sure that we're designing it appropriately from there. So with that, I will see you in the next video. Quality of service, or QoS, is a term that gets tossed around a lot within the networking world. We might be junior engineers and we hear our senior network engineers talking about the QoS policies. Or maybe you're in charge of a network and you know the pains of deploying quality of service in the infrastructure. But we do need to start our conversation from the ground level, which is flat out, why does everybody care about quality of service? I mean, what's the big deal? We've got big fat internet pipes these days and big fat LAN links. So do we really even need QoS these days? And before we just write off that question, let's be sure to answer that, because it's a legitimate question. Is it important in this day and age that we have quality of service? And even if we preclude that the answer is going to be yes, we do need to understand why. So in this video, we're going to take a look at why we so desperately need quality of service even in our modern networks. Let's take a look. I would argue that one of the primary reasons we even have networks today is to support various applications. These applications are often going to make our business work, or it's going to break our business if those applications go down. And when we think about critical applications, for example, especially critical applications that are time sensitive, we have to get the traffic out in an orderly fashion. One of the very first applications that comes to mind is going to be voice traffic or voice over IP. Beyond business applications, voice might be used to make emergency phone calls. What if we have a health situation on our hands and we need to get the medical professionals on site as quickly as possible? But even setting that aside, we need to be able to make phone calls as just keeping our business online in order to talk to our customers and to talk between our teams and such. But then we also have video. And video is going to be treated a little bit differently, because video, while it's much higher bandwidth than voice, it's slightly less time sensitive from the perspective that, well, I mean, if we're having a voice call, then my voice sounds like, if that's what my voice sounds like, you're not going to understand what I'm saying. Meanwhile, if we're having a video call and you can hear my voice fine, but my video is a little blurry, well, we can continue to have that conversation. The reality is that I need every single bit of that voice traffic to come through on time if possible, whereas a video call, even though it's as critical in a lot of situations, and yes, it does take up more bandwidth, so that's an interesting parameter, but it's less time sensitive. That said, we do have some critical natured applications that are less time sensitive even than video. We think about applications that are going to keep our business running, such as ERP systems or CRM tools. And if we're in the health industry, maybe we have electronic medical records or EMRs. So we've got a lot of different applications that are critical. In other words, if they go down, that's a problem. But at the same time, if it takes an extra second for a packet to go through, it's not that big of a deal. So we have critical time-sensitive applications, we have critical not time-sensitive applications, and then we'd have what I might call non-critical applications. When we're talking about non-critical applications, a lot of times I might cite email. Now email, depending on the organization, they might list that up here in the critical non-time sensitive category. Because if you're taking email orders from customers and you have to be very responsive to emails, well then email is going to be much more mission critical. But a lot of organizations these days are trying to make email less critical in the infrastructure, so maybe it falls into that category. We also would have internet traffic. When we think about internet traffic, we might think about streaming audio or video or downloading files. But again, when we turn this around and we think outside the box, what if we're a school system and as a teacher, I'm planning to show my students some kind of video that is hosted online, whether it's at YouTube or some educational site. And so I come in and now I can't teach the students the lesson plan that I had in mind because the internet traffic is not going through like it should. And so every application in our environment needs to be categorized based on our specific organization's needs. And that's not always an easy process. But if we can at least start by sorting it into these three primary categories of critical time sensitive, critical not time sensitive, and then non-critical traffic, at least gives us a starting place for what we want to see happen on our networks. Because the problem is that we're going to, at some point in our network, have a connection between two different networking devices, and we've got all of these applications showing up on this router, and those applications all need to share that link's bandwidth. So again, maybe I'm going to have voice traffic showing up, or video traffic, or maybe one of those other applications like ERP, and then emails and such coming through. All of these are going to be in contention with one another on this connection. Now make no mistake, these days we have a lot of bandwidth at our disposal. At a minimum, for most organizations, we're going to have a gig on a lot of our LAN links. But we could even go as high as 10 gig, or 40 gig, or 50 gig, or even 100 gig on our connections these days. So the question as posed in the intro is, do we even need quality of service anymore? Can't we just fling our traffic into a 100 gig pipe and allow it to carry all of this traffic forward? And partially the answer in some cases could be, yeah, maybe we can get away without quality of service. But the answer is that we will still need QoS, and there are two primary reasons for that. First of all, we are going to have periods of contention, meaning that we're going to have busy hours. Maybe this is the middle of the working day, and so we've got all of these applications going at the same time. But furthermore, not all of our connections in our network are going to be 100 gig. We might have wide area network circuits. We just got done in the ENSLD course talking about wide area networks. And in some cases, we might find ourselves with still a T1 or an E1 in certain parts of the world. And that's only 1.5 meg. That's nowhere near 100 gig. And so we're going to have to make the most of that bandwidth. However, even if we've moved past T1s, we might find ourselves with a 10 or a 20 meg MPLS circuit. Or furthermore, maybe we're in a metro area and we're trying to rely on wireless communications. In a lot of cases, wireless isn't going to give us the same amount of bandwidth that we can get from a wired connection. And unfortunately for us, we're not able to simply apply QoS to the parts of our network that need it and ignore the rest. We're going to have to make sure that we have an end-to-end QoS policy that allows for our traffic to handle contention when it arrives, whether it's because of a small pipe of bandwidth or because we have a lot of traffic showing up at once. So let's look at this interface and see what exactly is happening here. Because what we might find is that we have large packets coming through the network. Let's say this is a large 1500 byte packet. That's as big as Ethernet allows. And so we've got several of these packets lined up, and we're in the middle of transmitting one when a VoIP packet shows up. Now, yes, we're slowing this down to the microsecond level in some cases, but we do need to understand what's happening, because it does take time for the router to transmit a 1500 byte packet. And meanwhile, this voice over IP packet is sitting in the back of the line, not only waiting for that packet to get forwarded, but also these other packets that are in front of it. So we need to figure out a way to get that voice over IP packet out and moving on the network, rather than having to sit in line with the rest of these other packets that maybe these are non-critical packets in front of it. And for that matter, I mean, we'd love to pick on voice in the QoS world, but what if these packets in the front, let's say these first two are non-critical, but then what if this is a critical packet that's coming through? It doesn't matter that it's big, and what matters is its level of criticality. And we might want this critical packet to go in front of those non-critical packets. So we can't even base it on the size of the packet, because it's not always the small packets, in other words, the voice over IP packets and such, that we need to prioritize. Now next, we only have so much room in our router buffers to hold all these packets that we need to send. So what if our buffer is full, and then another packet shows up? Whether that's a voice over IP packet or another critical packet, we have no choice but to drop the new packet that showed up. So is there a way for us to get control over the traffic that we're dropping when our buffers are full? And in order to avoid tossing a rhetorical question out there, I will say that yes, we do have ways of getting around that, but we do need to understand that when it comes to our network designs. Lastly, here's a fun scenario. What if this router is provided by a carrier, and that carrier has told us, all right, we're going to give you a 20 meg Ethernet circuit via MPLS. And so this is 20 meg. How are they connecting these two routers at 20 meg? And the reality is that they're probably handing us off a physical Ethernet connection that maybe is 100 meg, but it might even be configured still for a gig or 1,000. So if that's a gig connection, but I can only send 20 meg of traffic, what's this router doing over here when it comes to sending traffic? It's going to assume that it can send traffic as fast as it comes in, because I've got a gig connection, and so maybe I'm sending 20 meg, but maybe I'm sending 25 or 30 or 100 meg. And we know that the carrier isn't going to like that, and so they're going to cut that traffic off. So what can we do in order to avoid the carrier from just indiscriminately dropping packets, which might be voice packets, might be ERP packets, might be internet packets? But wouldn't we rather have control over the packets that are getting dropped? And what we're going to find in the QoS conversation is that so much comes down to this idea of control. So many times we think of QoS as a way to prevent packets from getting dropped, but the reality, and this is important, is that in a lot of cases QoS isn't going to prevent drops from happening. That's not the goal. The goal of QoS is to give us control, and I already just wrote up at the top of the screen, but it's to give us control over what traffic does get dropped. Because if I have to drop packets, I'd rather drop the packets from the non-critical traffic category than from the critical traffic category. Now, the industry gives us two different paradigms for how we could go about deploying QoS. The first option, which is a little bit legacy at this point, is known as integrated services, or INTServ. Meanwhile, the QoS methodology we're going to probably use in most cases is going to be what we call differentiated services, or DiffServ. In the next video, we're going to start by exploring INTServ, and from there we'll take a look at DiffServ and how that operates. So the biggest takeaway from this conversation is probably simply that not all applications are created equal. Some applications are going to have a higher level of criticality, and we need to be able to prioritize those applications over the applications that are of lower priority. Second of all, yes, even in this modern era of networking, we do need QoS, and there's two primary reasons for that. One is simply that we're always going to have some level of low bandwidth links in our network, oftentimes in the wide area networking space, but then there will always also be periods of contention. It doesn't matter even if I have a 100 gig link, it doesn't matter what the bandwidth is. If my resources are low because I'm sending so much traffic across there, well then you can bet that I'm going to be glad that I designed that link with QoS in mind. And lastly, we do need those mechanisms in place in order to prioritize which traffic gets sent, and in some cases prioritize which traffic gets dropped. Remember, QoS is more about the control that it gives us. It's less about trying to prevent traffic from getting dropped, period. There's not much we can do about that in the networking world, but we can make sure that we are not dropping the traffic that we don't want to drop. I hope this has been informative for you. I'd like to thank you for viewing. Sometimes when we're studying something new in the networking world, it helps to study something old in order to know what the history is behind the technology. And that is the case with what we call integrated services, or INTServ. INTServ is a more legacy model for deploying QoS into the networking space, and it's really pretty cool how we go about doing it, because what we're doing is we're taking our packet switch networks and trying to give a little bit of that circuit switched goodness back to them as far as QoS guarantees are concerned. So in this video, we're going to explore INTServ as well as the protocol behind it, which is RSVP. Let's take a look. Think back to when you first started studying about networking, and we had this concept of circuit switched networks, that we harkened back to the days of having actual phone circuits in our homes before cell phones and such. And the idea is that one phone call would give us a single circuit, and that circuit was dedicated, meaning that it didn't matter if I was talking to my friend on the phone, or maybe I was pulling a prank on my friend and I said, hey, just a second, I set the phone down and I run off, and it takes my friend 15 minutes to realize I'm not coming back. And not that I ever did that, of course. And the great part about this circuit is that since it was dedicated, I didn't need a QoS concept, because this throughput was guaranteed for the entire duration that I owned that circuit. However, as you can imagine, this isn't very efficient. That was a lot of bandwidth, so to speak, that I was consuming, even though I wasn't actually speaking for 15 minutes. And this is why our networks over time evolved into packet switching architectures, which are far more efficient, but now we have to deal with this concept of contention, and quality of service is a required part of dealing with that. Well, the integrated services model, otherwise known as INTServ, is going to try to harken back to these days of circuit switch networks. We're going to try to deliver that quality of service guarantee that circuit switch networks brought us while still operating on packet switch networks. And at the heart of this model is a protocol that we call the Resource Reservation Protocol. Wait a second, Resource Reservation Protocol. Seems like that should be RRP, but it's not. We actually call this RSVP, the Resource Reservation Protocol. And if you are not used to this concept of RSVP, you might be wondering, well, Jeff, why isn't it RRP? Why is it RSVP? Well, RSVP is based on a French phrase that, and I'm going to screw this up because I'm not a French speaker, but I believe it's pronounced répondez s'il vous plaît. Now, I'm sure I botched that on some level, but at the same time, in the English-speaking world, even though it's a French phrase, we still use this. The phrase itself means, please respond. And we primarily use this phrase when we're inviting people to parties. We'll send out that invitation, and whether it's a birthday party or a wedding or some other celebration, we've got all of the information for that event, and then we say RSVP on it. RSVP with a phone number, an email address, some way of communicating back whether you plan to attend. And that RSVP is going to reserve your spot at the party to make sure that we have a seat for you and make sure we have a meal for you. And so this concept of creating a reservation is really what's at the heart of, hey, you guessed it, the Resource Reservation Protocol, which is again why we call it RSVP. So let's see this in action. Let's say we have a host that connects upstream to a router, and then let's just say that we've got a pretty small network here, so we've got 2 different layer 3 devices with a host on the other end that we want to communicate with. The idea behind RSVP is that I want to create a new flow with this remote host. Let's say we want to create a flow that's, let's just call it 10 kilobits per second. Nothing huge. But what we want to do is we want to reserve or RSVP our place on the network for this flow. We want to make sure that this link specifically has 10 kilobits per second available on it for us to consume. And the way we start this process is by sending an RSVP request upstream that we call a path message. We're trying to form a path through the network to the other side. Now that first router is going to receive that path request and process, hey, do I have enough bandwidth to guarantee that I can give 10 kilobits per second to this flow? And if so, I'm going to forward that path message upstream. Now, if that path message goes all the way through the network, then I'm going to get a reserve message or an RESV message back that more or less locks it into place to say, yes, we do have that bandwidth available, and we can all guarantee that you're going to get from one end of the network to the other without any contention. At that point, I start sending my traffic, and I do have a couple of things that I can keep in mind while this flow is in place. First of all, RSVP is allowed to police that traffic flow. If, for example, I start sending 15 or 20 kilobits per second, well, hey, wait a second, I only reserved 10. I've exceeded my reservation. That'd be like if I showed up to the party with 10 of my best friends, right? It's like, wait, Jeff, you only reserved 1 seat at this party. We don't have room for all of your friends. We don't have food for all of your friends. So we're going to police this effort of yours to crash this party. And so in the same way, we can police the traffic flow and drop anything that exceeds that. That's an optional configuration in RSVP. Furthermore, if I pull a prank like I did with my friend and all of a sudden this traffic flow goes idle, we're not actually communicating anymore, then RSVP is able to pull the reservation, say, okay, you're not going to use it anymore, therefore we're not going to guarantee that that flow still has throughput on this network. Now, I already said in the intro that we've evolved beyond the InServe model for a couple of reasons, but before we focus on why we've moved on from InServe, let's focus on the positives. Because there are some strong benefits to using this model, and I mean, a lot of people put a lot of effort into designing it, so clearly there must have been a reason why we'd want to consider using InServe. And the primary benefits are truly that we can actually guarantee traffic bandwidth on the network. More so than anything else, even with the DiffServe model, we cannot guarantee this 10K of throughput that we need to get through the network. We are only able to guarantee that with the InServe model. Furthermore, this gives us total control over what types of network traffic we're allowing onto our network. So with that out of the way, now we understand that there are going to be some downsides to this model. And the primary reason that we have downsides has to do with this concept of, well, we are going back to circuit switched mentality. And there is a reason why we moved from circuit switched networks to packet switched networks. And so when we think about how RSVP behaves, one of the downsides is going to be that this is an all or nothing approach. Meaning that if I request 10 kilobits per second of throughput on the network and my network can't reserve that for me, then I get absolutely no quality of service. I get absolutely no guarantee that my traffic will get through to the other side. Second of all, we're going to have major scaling issues because when we zoom this out and look at a very large enterprise network, we're going to have a whole lot more than just one host communicating with one other host. We're going to have a lot of different hosts that are all trying to grab RSVP guarantees, and at some point we're going to run out. And so we're going to have a lot of these flows showing up on the network that aren't able to get a QoS guarantee. And lastly is efficiency. Because yeah, we might be able to cut off some of these traffic flows if they're not fully utilizing their bandwidth, but at the same time, chances are this flow is not actually fully utilizing all 10 kilobits per second at any given time. And so we're always reserving more bandwidth for a flow than we are actually expecting them to send. And so because of the scaling, because of the efficiency problems, we probably need to think through, okay, how could we actually embrace QoS in a packet switch network using packet switching methodologies? And that is where the differentiated services or DiffServe model comes into play, which we're going to be talking about in the very next video. So when we look at this, I would argue that the takeaways are going to be pretty straightforward from this conversation. First of all, INTSERV is a model that guarantees bandwidth via the RSVP, or Resource Reservation Protocol. And the benefits are great. We've got the ability to, again, guarantee bandwidth. We can't do that with any other model. It gives us total control over our network traffic. However, the downsides are pretty significant. Well, we can't scale this very well. The efficiency of our network is very poor using INTSERV and RSVP. And as such, maybe instead of heralding back to the circuit switching days, we should really embrace our packet switch networks and find a methodology that's going to work better for it, which again is going to be differentiated services, or DiffServ, which we're going to be talking about right up next. I hope this has been informative for you, and I'd like to thank you for viewing. In modern networks today, we're not going to see a whole lot of INTSERV out there. Instead, we are going to see differentiated services, or DiffServ, deployed. In this video, we're going to take a look at how exactly DiffServ works, as well as what the benefits are and why we deploy them into our networks, as well as the challenges that come from them, and us as network engineers, what we have to deal with on a day-to-day basis when we're deploying quality of service. Let's take a look. Unlike the INTSERV model, the DiffServ model embraces the fact that we are running packet switched networks. We're not going to try to emulate circuit switch networks anymore. First of all, there is no reservation of resources in the DiffServ model. We recall with INTSERV, we were able to say, hey, my flow is going to take 10 kilobits per second, and I checked with all of the routers in the path, and I guaranteed myself that I'm going to have that traffic available to me, or at least that bandwidth available to me, as I push my traffic out. But that doesn't happen with DiffServ. Instead, we're going to classify our packets as they enter into the network. We're going to mark the packets with our classification, which tells the network how to treat them. So the classification is roughly equivalent to the treatment that I want to see for that packet on the network. But essentially, I'm simply expressing my desire to say, hey, this is how I'd like this packet to be treated. But once I send my packet into the network, there is absolutely no end-to-end agreement that that packet will be treated like I want it to be treated. Instead, every router in the path will treat that packet as it's been configured to treat it. In the DiffServ model, we call this per hop behavior, or PHB. The per hop behavior is per hop in the network. When I go from one network device to the next, the behavior of that device is going to be according to its own configuration, not because a bunch of routers have gotten together and agreed on how we're going to handle this traffic. So the way this happens is, let's say we have a host on the network and we're connected upstream to a router, and that router has an upstream connection to the rest of the network. So typically what's going to happen is this host is going to forward a packet upstream to the router, and at some point in this process, we need to classify this packet, whether it's the host that does it or the first router. But either way, we take a look at it and say, okay, how critical is this traffic? For example, is it voice traffic? Is it video traffic? Or is it web surfing traffic? And from there, we do something called marking, or in other words, tagging that packet. Typically in QoS, we call it classification and marking, and yet the marking concept is often referred to as tagging when we're talking about network configurations. So now that that packet has been tagged in a particular way, the packet gets forwarded up to the rest of the network, and we simply hope that the rest of the network is going to respect that tag and perform a per hop behavior based on how we want that packet to be treated. But the emphasis should be placed on the fact that these two routers, this one right here and the first one that it comes to, for example, they have reached zero agreement with one another on how that tag is going to be handled. Instead, we have to hope that they've been configured properly such that a QoS policy gets respected as the packet traverses the network. So let's talk about this tag for a moment. What does this tag look like? We have three main ways of tagging our packets. The first of which is called class of service. Class of service is a tag that goes inside the Ethernet header, and not just anywhere inside the Ethernet header. Specifically, it goes into the VLAN header. Now, we think about where VLAN headers go, and unfortunately in our networks, they don't go everywhere. They only go on trunk links. And so if our class of service tag only goes inside the VLAN tag, well, then we know that those class of service tags can only exist on trunk links as well. Now, the class of service tag gives us 3 bits to play with, and if my binary math is correct, that means that we have 8 different values, and those values would be 0 through 7. Next, we have this concept called IP precedence. IP precedence goes into the IP header, and it is also 3 bits in length. So once again, we have 0 through 7 for our values, this time with IP precedence. And lastly, we have a third option, which we call differentiated services. That should sound familiar, right? DiffServ. Differentiated services code pointer, DSCP. DSCP is also going to go into the IP header. In fact, it is going to take over for IP precedence. IP precedence is more of a legacy way of doing things back when we only reserved 3 bits in the header for QoS tags. DSCP looked at that and said, you know what, we actually have 8 bits in this field. We had 3 of them for IP precedence, and we kept 5 in reservation. And we probably don't need all 5 of those to be reserved, so let's take 3 more of those bits and use the 6 total to be DSCP. So in the end, we have the 3 bits from IP precedence plus the 3 new bits, and that equals 6 bits total that we can now use in DSCP. And hey, if my binary math is once again correct, that means we have 64 different values that we can use as DSCP tags. And those values would be 0 through 63. Now, as you can imagine, DSCP sort of taking over for IP precedence is going to mean that we don't use IP precedence a whole lot in modern networks. Instead, we're going to use class of service when we need layer 2 tagging, and DSCP for the most part when we're using layer 3 tagging. So we're going to tag our packets, fling them into the network, hope the network treats it appropriately. It sounds a little bit risky, so there must be some good benefits to this since this is primarily how we use QoS today. And indeed, there are some good benefits, so let's talk through those right now. First of all, this is an extremely efficient way of deploying quality of service into our network. We recall that some of the challenges of INSERV, for example, was that I could reserve a megabit per second of throughput and not actually use very much of that at all. So that's a reservation that is depriving other workflows from getting access to QoS guarantees. And hey, the more efficient it is, the better it's going to scale. Scaling this QoS architecture versus INSERV is no comparison. It is way more scalable and goes into even the largest enterprise networks in the world. And really, that's the end of our list of benefits, because these 2 benefits alone make it that we can use this model in our networks. And so that's great, but there are a few different challenges that we need to be aware of when it comes to deploying differentiated services. The first of which is that there are no guarantees. We already said this earlier. There are no reservations, and so I can't guarantee that my phone call, for example, is going to be given the bandwidth that it requires. So if we're not going to guarantee that a phone call can get through, then we need to have some mechanisms in place to make it as likely as possible that it will, in fact, make it through the network. And some of those mechanisms we're going to be talking about later. One of them would be congestion avoidance techniques. Another one would be traffic shaping, for example. Both of these are going to help us avoid dropping packets that we don't want to drop. Second of all, we do not have any kind of end-to-end communications among our network devices. In other words, they're not negotiating this with each other. We as network admins need to make sure that all of our devices are properly configured for QoS, as well as, by the way, all of our different domains. When I think about domains, I think about campus environments versus data centers, for example. We need to make sure that our QoS policy is consistent across these different areas. And unfortunately, making sure that our QoS policy is consistent among all of our devices can be a big challenge, because when we look at QoS configuration on a Catalyst 3K versus a Catalyst 9K, that's a huge difference, not only in the configurations that we use, the commands themselves, but also the underlying hardware architectures that determine how many queues, for example, are on each interface and such. And by the way, not just Catalyst 3K versus 9K, but also Nexus 3K versus 9K. Even inside the data center space, we have these problems. And switches are different than routers. And so there's a pretty big challenge that we as network admins get to face here when it comes to making sure that all of our devices are properly configured and tuned for QoS. And lastly, what about the policy itself? Have we taken the time to define a policy that determines how we configure our different domains in our devices? And also, how do we maintain this policy over time? Because imagine that we go out there and we configure a beautiful QoS policy, and we've guaranteed that 10% of the network bandwidth is going to be reserved for voice over IP traffic, let's just say. And then about 3 months in, maybe some network changes have happened, and all of a sudden 10% just isn't enough. And so we decide that, you know what, we're going to guarantee 12% of bandwidth to the network. Well, if I could go into a GUI interface and say, you know what, instead of 10%, let's just make it 12%, well, life would be grand, wouldn't it? But for those who have experienced this, you and I know that we're going to have to go out to all of the different devices in our network and make sure that, yeah, whether it's a Catalyst 3K or a Nexus 9K or an integrated services router, that we are properly changing the configuration just to make this small little change of just a 2% difference. So unfortunately, nothing comes free. We do get some stellar benefits with the DiffServ model, but we do need to be aware of the challenges that we're going to face as network admins deploying it. So as we can see here, DiffServ is very different from integrated services. First and foremost, DiffServ offers no guarantees or reservations whatsoever. Instead, we are going to rely on classification and marking and that per hop behavior concept. We're essentially going to tag a packet with the desired behavior and send it into the network and hope for the best. Second of all, we are going to tag our packets with either the class of service value that goes into not just the Ethernet header, but specifically the VLAN tag portion of the Ethernet header, so only on trunk links, as well as IP precedence and DSCP from a layer 3 perspective. Third, the benefits of diffserv are all about efficiency and scaling. This was intserv's biggest problem, is it didn't scale well. It wasn't an efficient use of resources. And so diffserv embraces packet switching and says, all right, we're going to just get the scaling and the efficiency of packet scaled or packet switched networks, but understanding that that's going to bring some challenges as well. And specifically, those challenges are primarily going to get wrapped up into this concept of deploying end-to-end policy. Because as we've seen through this conversation, we have to deploy one policy across many different devices and many different domains, and making sure that it's end-to-end consistent and we're treating at every single hop a particular traffic flow appropriately. Well, that gets to be a challenge for us as network engineers. Fortunately, we can do this, but it just, for us as the designers, we need to make sure that we are thinking about that policy, making sure the end-to-end is established, and then just simply taking it one step at a time and making sure our devices are properly configured. I hope this has been informative for you, and I'd like to thank you for viewing. You say tagging, I say classification and marking. The official term for tagging packets in the QoS world is, again, classification and marking. We're going to classify a packet, decide how exactly we want to treat that, and then we're going to tag it appropriately. In the last video, we explored 3 different ways of tagging packets between class of service, IP precedence, and differentiated services code point, DSCP. That's a mouthful. And in this video, we're going to dive deeper into each one of these tagging methodologies. Let's dive in. Let's start off by talking about class of service. Class of service, recall, is that tag that goes into the Ethernet header, and we're going to call this 802.1p. 802.1p uses 3 different bits that are inside of the 802.1q header. Now this 802.1q header is only going to exist on trunk links, so we need to make sure that we understand that QoS, by extension, is going to work on trunk links only. And as such, we need to make sure we don't accidentally lose our class of service information. For example, if we think about a host connected into a switch, and maybe we connect that switch to another switch, except we accidentally configure that as an access link. Well, everything might work here as long as we're only using a single VLAN, but our QoS tags here will get lost because when the packet comes in and gets classified, it'll get put out onto this access link, and, well, we don't have room for a QoS tag on an access link. The other thing to consider is that if we're going to get onto a router, let's say, and that router has an upstream T1, well, this T1 is not Ethernet, and as such, it doesn't have room for a QoS tag. So QoS is generally considered useful only for the sake of identifying traffic, and what we like to do is take QoS and convert it into IP precedence or DSCP, because IP precedence and DSCP are both in the IP header, and they're going to survive regardless of whether it's a trunk link or a T1 and such. Now that 802.1q header gives us 2 bytes, that would be 16 bits of information. 12 of those bits are going to go to the VLAN ID, and 1 is used for a flag, and that gives us 3 bits left over to use for our class of service. That means that our values can be from 0 to 7, that gives us 8 values total, but at the same time, we don't quite get all 8 of these values to use, because specifically 6 and 7 tend to be reserved for network control traffic. This would be for packets such as EIGRP hellos and such. They're going to get automatically tagged with a 6 or a 7 on the link, depending on which part of the process we're talking about. We also typically reserve 5 for voice traffic, and by default, all other traffic gets placed onto 0. So if we don't specify any other kind of classification of the traffic, we can expect a QoS value of 0 to be used. Now this conversation is pretty well paralleled by the concept of IP precedence. IP precedence is going to leverage the IP header to store the tag, and as we've mentioned, this means that we're going to have end-to-end QoS, because in most cases we're not swapping out IP headers like we are Ethernet headers. In a lot of cases, what we're going to do is we're going to look at the fact that we have a packet coming in on a switch whose class of service might be a particular value. Let's say the class of service is 5, and we're going to want to translate that over into IP precedence. So we'll take that QoS value of 5 and add IP precedence of 5 onto that packet. This works great because, just like class of service, we get 3 bits of information. And stop me if you've heard this before, but that means we have 0 through 7 as our possible numbers, with 6 and 7 reserved for network control. We use 5 for voice, and we use 0 for default. So in the end, QoS and IP precedence are going to seem very similar with how we tag traffic, and especially the numbers that we're using. Now we get to talk about the fun one, differentiated services code point, or DSCP. DSCP is actually going to give us 6 bits, unlike the other 2 that we've talked about, which gives us a value from 0 to 63 that we can use for the tags. The reason that we get 6 bits is because when we look in the IP header, there's an entire byte that's used for type of service. And originally, the first 3 bits were reserved for IP precedence, and 5 bits were reserved for future use. Well, the powers that be looked at that and said, you know, we don't need all 5 bits reserved. Let's give 3 more to quality of service and keep 2 of them back. These 2 now, by the way, are used for flags, which gives us 6 total bits, again, for DSCP. So here's the question. When we have 6 bits, that's 0 to 63, this feels a little bit like we have too many values. We're human beings, we're not computers. And so for us to design a QoS policy around 64 different possible tag IDs, and for the most part, we're still only going to use in that range of 8, maybe 10 or 12 or something along those lines. And because of this, the industry decided that we're going to standardize some of our DSCP values in order to make them easier to use. Think about it a little bit like a website compared to an IP address. It might be really hard to remember a specific DSCP value, but I can remember the name of a value and then apply policy against that particular name. And the industry gives us several different names to talk about. The first of which is going to be the class selector. The class selector is a fairly straightforward one. We get 8 different class selectors, so we call them CS0 through CS7, and they're going to be equivalent to IP precedence 0 through 7. Remember, we are using the same 3 bits that IP precedence does, and so we can kind of break them down and think about the first 3 versus the second 3. So when we talk about class selector 0, for example, that's going to take the first 3 bits, set them all to 0, that's the IP precedence bits, and no matter what in all of these, we're going to keep the second 3 bits set to 0 as well. Next, we could consider class selector 1. We set the first 3 bits to be equal to 1, that would be 0, 0, 1, and again, we leave the second 3 bits set to 0. For class selector 2, same thing. We can use these bits by setting them to 2, and then the second set of bits we leave as 0. And we can do that all the way down to class selector 7. At class selector 7, I just set all of these to 1. That's the equivalent of 7. And then we set the last 3 to 0. So what we see here is we're basically not using the DSCP bits, and we're only using the IP precedence bits. This is why we say that it's roughly the equivalent of them. If we were to bring a tag in that has a COS value now of 5, and we wanted to map that to DSCP, usually what that means is we're going to map those to the class selector value. We're not even going to use the extra 3 bits, we're simply going to use the IP precedence bits and keep the second set of 3 bits set to 0. But that's no fun, we want to use those extra 3 bits. And one of the ways we can do that is with the second category that we call assured forwarding. Assured forwarding gets a little bit interesting. The way the nomenclature works is we say AF for assured forwarding, followed by X and then Y as 2 separate numbers. The X is going to be our priority level, and the range is going to be from 1 to 4. Meanwhile, Y is going to be our drop rate, and the higher the drop rate, the more likely a packet is to be dropped. And we're going to have that be a value of 1 through 3. What we're going to find is when we break down the DSCP bits, those 6 separate bits, we're going to identify the first 3 as X, then the next 2 as Y, and then we're always going to end with a 0. Why are we ending with a 0? Well, because if we end a binary number with 0, then that makes it an even number. And the reality is that we've got so many different numbers out there, 0 to 63, we only need a handful of them. So let's just use the even ones, and that makes our lives a little more simple. So when we're talking about assured forwarding values, the way we write this out is, again, AF followed by XY. So we might have, for example, AF11, or AF12, or AF13. Remember, that second digit can go from 1 to 3, but also the first digit can go from 1 to 4. So we could also have AF21, or 22, or 23. And we can keep this going and go to 31, 32, and 33, followed by 41, and 42, and 43. The higher the first number, the higher the priority. But the higher the second number, the higher the drop rate. So it's actually better to be in a category, let's say 41, than 43, because 41 indicates that we should have a lower drop rate than 43. So that's great. Let's say I want to classify my traffic as AF22. What exactly am I doing with DSCP if I'm categorizing my traffic as 22? Well, this is why we look at this part right here, where we're breaking down the 8 different bits. If I'm going to make it AF22, AF22 is going to make the first 3 bits 2. So I will make them 0, 1, 0, that's binary for 2. And then YY also needs to be binary for 2, that's the second number. So in this case, we would set 1, 0, because we're taking them individually as a set of 2 bits, and we're not taking the 0 into account that's there. So then we always end with a 0, because again, it's always even. Now that said, the DSCP value itself is derived from all 6 bits. So if I want to know what the DSCP value is for AF22, I need to convert this 6-digit binary number into decimal. So this is the ones field, this is the twos, this is the four. So we have 4, and then we have 8, and then 16. So this would be 16 here plus 4 is equal to 20. So AF22 is the equivalent of a DSCP value of 20. Let's look at one more example. Let's take AF31. 31 is going to be 3 for the X and 1 for the Y. So 3 in binary is going to be 0, 1, 1, followed by 1 in the YY, so that'd be 0, 1, followed by another 0. So we do the binary math again. We say, okay, this is the ones, this is 2, so we've got 2 here, 4, 8, and 16. So 16 plus 8 plus 2, that would be a DSCP value of 26. In the end, all of these values here are just for us humans to be able to read and understand. I want to be able to apply policy again against AF33 traffic. I want to be able to configure my router so if a packet shows up and it's got something like AF32 configured, then I would be able to process that and apply policy against that without ever having to take it back to its DSCP values. Now, that said, if Cisco on the Encore exam wanted to ask us, hey, what's the DSCP value of AF32? Well, then we better be prepared to answer that question. And here's how we answer that. We use the equation 8x plus 2y. And the reason for that is because the x's here are in the 8's column and the y's are in the 2's column. So if I look at AF32, I would say 8 times 3 plus 2 times 2. That would be 24 plus 4, so AF32 has a DSCP equivalent of 28. So keep this equation in mind, 8x plus 2y, because if you're given AF values on the Encore exam, and again, they want that DSCP value, that will allow us to very quickly convert that and move on to the next question. Now, we have class selector, assured forwarding. We do have one more to discuss, and that would be expedited forwarding, otherwise known as EF. Fortunately, expedited forwarding is a very quick conversation. What we want to do is we want to have the highest possible DSCP value that we can assign to quote-unquote normal network traffic. So let's think about this for a moment. We've seen several times that we don't want to use, for example, CS6 or CS7, because 6 and 7 are reserved for network control traffic. We also like to use even DSCP values. So what is the highest DSCP value that we can use that is both even and doesn't interfere with anything CS6 or above? And the answer to that is going to be DSCP 46. CS6 is 48, and we want to grab the next highest even number, and that's where we get 46 from. In most networks, we are going to map our voice over IP traffic to expedited forwarding. And so again, on the back end, that's DSCP 46, but for us configuring and managing routers, for example, all we have to do is apply our policy to EF. And applying a policy to EF, or AF22, or AF43, or CS0, whatever we're applying our policy to, it's a lot easier to use these naming conventions than it is to use a raw DSCP value. Now, if the DSCP conversation is making your head spin a little bit, then don't panic. That's pretty normal. It takes a while for us to wrap our brains around how exactly DSCP values are getting mapped to these different names. But let's back up the conversation a little bit, because first of all, we need to remember that QoS and IP precedence, they are based on 3 separate bits instead of the 6 that DSCP gives us. So we have the range of 0 to 7, with 6 and 7 usually getting reserved for network control traffic and such. Second of all, now let's talk about DSCP. We have those 3 different categories that we place our DSCP names into. The first of which is class selector, or CS. CS 0 through 7 is going to map to IP precedence 0 through 7 because we're going to use the first 3 bits that IP precedence used, and we're not even going to use the second 3 bits. We're just going to keep those as zeros. Now, DSCP assured forwarding, that's where things start to get pretty interesting, because now we're going to use the first 5 bits. And yeah, I don't know why we're not using the last one other than just to make them all even and make them easy to calculate. But either way, we're going to use those first 3 bits as the first digit of our assured forwarding, and the second 2 bits, or the next 2 bits, I suppose, as our second number. Keeping in mind that equation, 8x plus 2y. If you can remember 8x plus 2y, you will always be able to convert an assured forwarding number into a DSCP value. And lastly, we only touched on it briefly because it's pretty straightforward. Expedited forwarding, there's one value for it. It is DSCP 46. It is the highest DSCP even, I should say, the highest even numbered DSCP value that we can use that is short of that 6 and 7 range. So class selector 6 and 7, we don't want to touch those. They're reserved for network traffic and such. So 46, that's as high as we can go for normal network traffic. I hope this has been informative for you. I'd like to thank you for viewing. We love deploying routers and switches into our network and having those interfaces light up and sending packets. But what actually happens on an output interface when we get a bunch of packets destined to go out that very same port? In this video, we're going to explore how exactly that functions and how we can leverage queuing and scheduling in our QoS designs. Let's take a look. Let's say we have a router, and that router has a lot of different input interfaces, bringing in lots of traffic, whether it's on the internet or maybe inside our own networks. And a lot of this traffic is destined for the exact same interface. What exactly is happening on this interface? If we were to zoom this out and take a look, what we'd find is that we can't send all of those packets at once. We can really only start sending one packet at a time, and meanwhile all the other packets that are destined for that interface are just going to have to get in line, so to speak. And we have a name for this, and that would be a queue. All of the packets are going to wait inside of a queue to be sent. But we do have a problem around this idea of having a single queue. And that is that what if this packet right here is more important than the packet that's in front of it? We have no way of reorganizing the packets once they're inside of a single queue. And the solution to this is not to have a single queue, but to have multiple queues. Let's see how this might work. Let's say you and I go to an amusement park, and we're getting in line for a roller coaster. Yeah, this is a roller coaster. Don't worry about it, I'm sure it's safe. And so you and I and all of the rest of the people in the amusement park, we're getting in line. And I don't know if you've ever been to an amusement park getting in line for a roller coaster, but I tell you what, these lines can be very, very long. And they are single file for the most part. And we're going to end up waiting. Let's say we're here in the back. We might wait a half an hour or 45 minutes, even up to 3 or 4 hours for some of the most popular roller coaster rides. But here's the problem. Let's say this is at Disney World and 2 Disney characters were to show up. Let's say Cinderella and Prince Charming come and they want to get in line. Well, these 2 individuals are what we call very important persons, or VIPs. And the park wants to treat them very, very different and very, very special because their opinion matters a whole lot more than you and I who just happen to pay 20 bucks to enter or what have you. But the problem is every time a VIP shows up, if we had to step aside and let the VIP through, and that would just be awkward and it wouldn't be a whole lot of fun for any of us involved. So instead what they're going to do is simply say, you know what, we're going to create a VIP line. So don't even get into that other line, Cinderella and Prince Charming. You're going to get into the VIP line. And maybe they brought 2 of their friends as well. This way, when the next person gets to go onto the roller coaster, the park can choose to take a person from the VIP line rather than the other line. In fact, that park could choose to take all 4 of these individuals from that line, or they could potentially take 1 from each one, maybe alternate back and forth. However they want to do it is fine. But it gives them access to the important packets. Or, I guess, persons in this case. Over the last 15 or so years, we've seen a lot of amusement parks embrace this methodology. Not so much that a Disney character is going to show up, I don't think that we can expect that. But the parks allow customers to purchase VIP passes that give them special access to rides. And in some cases, you can even schedule a ride. And so if you schedule it and show up at the right time, then you get put into the VIP line. And your wait is a whole lot shorter. But here's the question I need to ask. When we consider this roller coaster and how many people get to ride it, does having 2 queues enable us to have more people riding this roller coaster? And the answer is going to be no. We're not going to be able to fit any more. If we can fit 500 people on this roller coaster a day, it doesn't matter whether we have 1 or 2 queues. We can still only continue to support those 500 people. And so even though we're not sending more people onto the roller coaster, what we do get is we get control. We get the ability to choose up at the front who gets to get on that roller coaster, for example. But then we also get control in a different place. And that is that what happens if we have too many people in line? Let's say maybe we have to cut people off after a certain amount of people are in line. Well, now we actually have control on the backside as well. So when a person shows up and the line is too long, well, we can say, sorry, you don't get to get into line at all. But hey, if a VIP shows up, well, we don't want to send them away and we can allow them to get in line. So it gives us control at the front of the line and it gives us control in the back of the line. And as we relate this back to QoS, we're going to find that same thing. We get control at the front of the queue, and we get control at the back of the queue. So let's talk about these queues. Let's say we have a router, and we've got multiple queues. Let's just draw out, let's say 4 different queues here. And now we get a packet that has shown up, and it's destined for this interface. Keeping in mind that all of these queues belong to a single interface, so maybe this interface up here on our drawing. What we want to do is we want to look at the tag on that packet. And we just spent a whole lot of time in the previous video talking about all the different tags that we might have, whether it's class of service, IP precedence, or DSCP. Either way, we're going to use that tag to tell us which of these queues we want to send that packet into. So as we accumulate packets here, what we're going to find is that we have a lot of different packets showing up in these different queues. At any time, one of these queues might be totally full, and another queue might be totally empty. Now, as for how many of these queues we get, well, it's going to depend on the platform. A lot of routers create these queues in software, and so we can create 8, 12, or 16, or in some cases even more queues if we desire. In a lot of platforms, though, it might be hardware-based, so we have a lot of switching platforms that lock it down to 4 different queues or what have you. So we as the network admins might get to choose, we might be stuck with a certain number, but either way, what we want to do at this point is to go through these different queues and assign them different amounts of bandwidth that they get to consume. So let's just make this simple. We'll say 10%, 20%, 30%, and 40% for these respective queues. That's how much bandwidth we want to assign of the total bandwidth. If this is a 10 gig circuit, then we're delivering 1 gig, 2 gig, 3 gig, and 4 gig respectively. Furthermore, we can place one of these queues into a priority status that says, hey, the packets that arrive in here, it's not just about the bandwidth anymore. They are so important that they need to go out first. So now we have our policy in place, it's time to enforce it. And the process that enforces it is called the scheduler. The scheduler is going to go through these different queues on a given cycle and decide which queue gets to send its packet next. Think back to the park situation. There's probably a person up here who gets to decide, okay, which queue am I pulling from, right? Am I pulling it from the VIP queue? Am I pulling it from the normal queue? If it's a priority queue, then I might pull everybody out of the VIP queue, regardless of how many people are in that line. But if not, if it's a more of a balance with bandwidth, I might take 1 VIP and 1 person, or maybe 2 VIPs per other queue. And so we're going to do the same thing with our router. Keeping these bandwidth amounts in mind, we might pull 1 packet from Q1, 2 packets from Q2, 3 packets from Q3, and 4 packets from Q4. This would assume that all of the packets are created equal, so they're all the same size. This would give us roughly a 1 to 2 to 3 to 4 ratio. However, not all packets are created equal. They're not all the same size, and so part of the job of the scheduler is to recognize that we're tracking bandwidth, not just the packet count that goes through. Furthermore, we may find that one of these queues is empty. So let's say Q2 here doesn't even have a packet. Well, we don't have any packets to service, and so that actually gives more bandwidth to the other queues. The scheduler can say every time I was going to send a packet from Q2, for example, I will pull that packet from a different queue instead. So that way we can all share the bandwidth. When I need the bandwidth, I get it, but when I don't need it, I give it to the other queues. Now we're going to be covering more about queuing and scheduling in the next skill, but for now, here are the things we need to keep in mind. First of all, queuing is how we buffer packets when we're trying to send them out in interface. And we realize that a single queue isn't a good idea. We don't have any control over who's getting sent out. That's why we want to use multiple queues. We think about that roller coaster example and the VIP queue. And we want the exact same concept, but not just 2 queues. We want as many queues as we desire in our network designs. So we're going to bring packets in and match them to queues based on their tags. Those tags are, again, QoS or DSCP or IP precedence or what have you. And those tags we use to assign to a queue. And then the scheduler is going to choose which queue to service at any given time. And it's going to decide that based on the configuration that we give it, specifically regarding whether the bandwidth is set a certain way or whether we're using priority queues and such. I hope this has been informative for you, and I'd like to thank you for viewing. We have reached the end of yet another skill, so let's review what we've learned by taking a quiz. First up, out of 4 questions, what RSVP message types are used to request and confirm resource reservations? Well, as we'll recall, we are going to use path messages to send a request upstream. That path message is going to get forwarded from router to router, from network device to network device, until we've established that yes, indeed, we can perform this resource reservation. And in order to lock that in, we're going to send a message type back that is the reserve message, or RESV. So path and reserve messages, these are our answers. Question 2. How many bits is each type of QoS tag, and in what header is it located? Well, class of service is 3 bits, and that's going to be located not just in the Ethernet header, but specifically in the 802.1q header that contains the VLAN tags. So as we recall, we've emphasized many times, if the VLAN tag isn't going to show up, in other words, it's not a trunk link, then neither will the class of service tag. Meanwhile, the IP precedence is also going to be 3 bits, but this is located in the IP header. And lastly, DSCP uses the same 3 bits as IP precedence, but it adds 3 more bits, so we get 6 bits total, which again is in the IP header. So generally speaking, we're going to use class of service for our local Ethernet segments, but really for end-to-end QoS policies, we're going to rely on something out of the IP header, so either IP precedence or more likely in modern networks, DSCP. Next up, what DSCP values are used for each of the following tags? And by the way, be sure to pause this video in order to take the time to run the calculations yourself. When it comes to class selectors, that is simply IP precedence. So if IP precedence has a value of 5, that would be a 101 for the first 3 bits, and we're not even using those last 3 bits. Ultimately, since whatever this number is, it's in the 8s column, we're simply going to multiply that number, 5 in this case, by 8. And so in this case, 5 times 8 makes our answer 40. DSCP 40 would be the answer for class selector 5. Now for assured forwarding, we need to remember that algorithm, 8x plus 2y. And as such, when we have AF13, x is 1 and y is 3. So 8 times 1, that's 8. 3 times 2 is 6. So 8 plus 6 should be 14. DSCP value of 14 for AF13. And meanwhile, we're going to apply the same algorithm to AF42. So 8 times 4 is 32. 2 times 2 is 4. So our answer here would be 36. And lastly, expedited forwarding doesn't even need a number because it is always going to be DSCP 46. So if you got all 4 of these right, then congratulations, you know how to convert these DSCP tags back into DSCP values. But if you missed any of them, then be sure to go back and make sure that we understand how exactly we derive the DSCP values, because that is absolutely fair game on the ENSLD exam. Question number 4, and it's our last question. By leveraging multiple queues, we can prevent packets from getting dropped by transmitting more packets onto the wire. True or false? Well, the answer here is false. I want to make sure we're absolutely abundantly clear that quality of service does not mean that we're not going to drop packets anymore. We are still going to have to drop just as many packets, but instead what QoS gives us is it gives us control. It allows us to choose which packets we drop and which packets we don't. It's a big misunderstanding in the industry that QoS prevents us from dropping traffic. We need to absolutely understand this fundamental concept that really what we're seeking is that level of control. Well, that wraps up this quiz. If you found yourself missing any of these key pieces of information, then be sure to go back and watch the appropriate video in order to fill any of those knowledge gaps. Otherwise, congratulations on completing Select QoS Strategies. I hope this has been informative for you. I'd like to thank you for viewing.